Now it's time to start the last topic of advanced higher physics, and that is inductors. So the first question is, what is an inductor? And an inductor is a circuit component that resists changes in current by allowing an EMF, electromotive force, which you should remember from higher, to be induced by magnetic fields. So, question, where do these magnetic fields come from? Magnetic fields come from the fact that we have moving charges. So if we've got a current in the circuit and that current is changing, we have most definitely got a magnetic field, and magnetic field put through or across a certain type of component known as an inductor will induce an EMF, and that EMF will be directed such as it resists the change in current that created it in the first place. Now, the other answer to this question, and the much less interesting one, is a coil of wire, because almost all inductors are simply a coil of wire, which is why the symbol for an inductor looks very much like a coil of wire, like so. That's the symbol for an inductor, and this is the symbol for an inductor with a core, and that core material is usually soft iron, which is fairly easy to magnetize. We already know a little bit about magnetic induction because we studied Ampere's law in Unit 2 of the Advanced Higher Physics course, and we should remember from that that Ampere's law says that mu naught I equals the integral of B dot dl. In other words, if we integrate along the length of the magnetic field lines, we will get an equation that will tell us what the magnetic induction B is for a given scenario. For example, at a distance r from a long straight wire, we should remember that the magnetic induction will be mu naught I over 2 pi r, and we should also remember that for a solenoid shape, which conveniently is the shape of an inductor, B, the magnetic induction, will be mu naught N I over L, where N is the number of turns and L is the length of the solenoid. Fair warning, as we go through this topic, we're going to end up with about 3 different L's and about 3 different E's. So you're going to have to be very careful about the context of which letter is which in which circumstances. Nothing we can do about it. It is what it is. The next concept we have in this field of physics is a thing called magnetic flux, and that is going all the way back to James Faraday, which is 1700s, late 1700s I think it was, and that is the integral of B dot dA. So the magnetic induction, again, but instead of a length, this time it's an area, and that will give us, in the simplest possible case, phi equals BA. So far so good. So that is the magnetic flux. The magnetic induction area. The area will be in meters squared as usual, the magnetic induction will be in Teslas as usual, which means the magnetic flux must be in Tesla meters squared. So far so good, but what does this magnetic flux business actually refer to? Well, the magnetic flux refers to how many field lines are passing through a given area. So if I have a nice square-shaped area like so, and in that area of space, think of a two-dimensional square suspended in the air somewhere, there is a given number of magnetic field lines passing through that area, then the greater the number of magnetic field lines passing through the area, the greater the magnetic flux. Passing through a given area, the greater the magnetic flux. The problem, of course, arises if it's not a nice simple area like a square or a rectangle or a triangle. So that's where we have, as written on the previous page, phi equals the integral of b dot dA, where dA is an infinitesimally small segment of the area, and that's fine as far as it goes. But there's also the other snag whereby nobody said the magnetic field was constant, because, as we'll remember, the magnetic field, to be specific, the magnetic induction depends on the current, and the current isn't necessarily constant. It could be a time varying current, like an AC current. So if we wanted to be ultra precise, we would say that this was the integral of b of t dot dA, and then we'd have some sort of equation that would describe how the magnetic field varied with time. That would probably be also one that was current with time, because, for example, if b equals mu naught I over 2 pi r, and that's a time varying current. So now we come to Faraday's law, named after James Faraday, and it's important to remember he was doing this long before Maxwell came up with these famous equations. So by experiment, by observation, by measurement, Faraday was able to determine that the EMF produced in a solenoid, aka an inductor coil, was equal to negative, we'll come back to why that's there later, n, the number of turns in the coil, d phi by dt. So the rate of change of flux. So EMF equals rate of change of flux, or at least the magnitude of it does. Now here we have what we can call the baby steps version of the equation, which is to say that EMF is equal to negative, again we'll come back to why that's there in a minute, n for the number of turns of wire in the coil, the final flux minus the initial flux divided by the time it took for the magnetic flux to change. So how did Faraday determine this? How did he codify it in a formula once he'd done his experiments and his measurements, if this was all happening before Maxwell got his equations of electromagnetism put together? Well, what Faraday did was he said, let's take the smallest possible current. That'll be one charge, one electron moving in a circular path in a magnetic field. And let us say that it's also moving in an electric field. And let us say that these electric and magnetic fields are perpendicular to each other. So having decided that that was the case, we could say that F equals QE, which also equals QVB, and you should remember both of these from Unit 2. That meant that E, the electric field, equaled VB the magnetic induction. Now we can go in two roads from here. So let's take a slight detour. That means that V equals E over B, and this is called the drift velocity of the charged particle. And if we remember that in, say, a nice simple situation like a pair of parallel plates, we could then substitute in whatever E was. So parallel plates. We could say V, the velocity, was equal to V, the potential difference between the parallel plates, over B, the magnetic induction, and D, the distance between the plates. The other route that we can take from here, the route that Faraday took, is to say, indeed, E in a nice simple scenario with parallel plates is V over D equals VB. Remember, V for potential difference between the plates, V for velocity of the charged particle. So we've got parallel plates with an electric field, and we also have a magnetic field perpendicular to the electric field. And then V for potential difference equals VBD. So far so good, it's just that thing down there, but slightly rearranged. Until you make the observation that V is velocity, which is meters per second. So that's length over time. So V equals B for magnetic induction, D for distance between the plates, L for length over T for time. So that gets you V equals BA over T. And lo and behold, isn't BA equal to magnetic flux? So magnetic flux over time. Now, this equation and this equation, more importantly this equation, are obviously not exact matches for each other, but what they do have is here and here we have the same units. So Faraday knew he was on the right lines, and he knew from experiment that if the magnetic flux didn't change in some way, then he didn't get an EMF. So from experiment, with a bit of theory to back it up. This is the case we use for if we were moving the circuit through a magnetic field, which is pretty much what Faraday was limited to at his point in history. Moving circuit through magnetic field. Also importantly, we don't have the minus sign yet. Faraday could very easily deduce that if he would done this extrapolation for a single loop of current, if he had multiple loops of current on his coil, then N for multiply by the number of loops of current. But the minus sign wasn't there. And Faraday, in his lifetime, didn't actually know that the minus sign should be there. And to be honest, he probably wouldn't have cared, because the magnitude of the EMF was turning out to be exactly what he determined. It was another chap by the name of Lenz that explained to us why the minus sign ought to be there. And what Lenz said was that this minus sign needed to be here because the direction of the EMF that was induced by the changing magnetic flux was always the direction that would oppose the change in the magnetic flux. So let's get that written down because it's important.